Alright, folks, welcome back from the long weekend. Everybody ready for the big test tomorrow?
No.
That's okay, that's why we have a review day today. So, I encourage you to have at least a piece of paper out to write on and a writing utensil. We are going to go through our review session today, and you should be all set to go for the test tomorrow. If you need extra paper, I have some in the back above the microwave behind the glass. If you need an extra pencil, that's in the back too. So feel free to use those. Alright, so this is the sort of thing that you'll see on page 1 of the test here. So we've got two objects, and their motions are represented on a position-time graph. And from this position-time graph, I want you to show me two things. I'd like you to show me what the velocity-time graph for each object is, and how are the motions of A and B different. So this would be something you're writing, and this is something that you're drawing. So do the best you can. I'll give you just a couple of minutes to try this out. So the question again was, this is your position time graph for these two individual objects. What is the velocity time graph going to look like for those? So we'll start with that one, then we'll move on to how the motions are different. So remember, on a position time graph, the slope represents your velocity. So the slopes here are going to tell us how to draw the velocity time graph. So you can see object A has a constant positive slope, so that means on the velocity time graph, object A would be up here. Object B has a slope of 0, so it will be 0 on the velocity time graph. And that's what your answer would be for the velocity time graph. So then the question would be, how are the motions of these two objects different? How do we describe that? I would probably just say that object A is moving, object B is not moving. Again, you can find that just by using the significance of these slopes. This is a positive slope, so it's got a positive velocity. Slope of 0, so it's got a velocity of 0. Object A is moving away from the origin. Object B isn't moving at all. Questions on this one? Let's try another one of these. There will be 2 of these on the first page of the test. So now do the same thing for these two objects. Draw the velocity time graph, and then explain how the motions are different. So first off, let's take a look at that velocity time graph. We've got object B, it's a pretty shallow slope. We've got object A, which is a pretty steep slope. So of course, the steeper your slope on a position time graph, the greater your velocity value is going to be. Now both of these slopes are negative, so that means they're going to have negative velocities for both of them. Because slope A is bigger than slope B, that means this negative value will be larger than this one. So object A, big negative slope, that means it's got a big negative velocity. Object B has a negative slope too, but it's not quite as big. So object B is going to be not quite as large on the velocity time graph there. in terms of comparing their motions, object B is traveling slower than object A. So anything along those lines would be just fine. They're both going in the negative direction towards the origin, but A is moving faster than B. Questions on these? All right. I smell a lot of 0 wrongs on page 1 of the test tomorrow. Now, in the same way that you were asked to do things qualitatively, there is one part on the test where you'll be asked to draw a graph quantitatively with numbers. And remember, that is on your formula sheet if you forget the difference between qualitative and quantitative. So, let's say we're given a velocity time graph here. We'll do that. So this is our velocity time graph. We have a straight horizontal line at 2. Then we've got a straight horizontal line at 0 and a straight horizontal line at -1. So the question for something like this might be to draw the corresponding position time graph, but draw it with numbers. So take about 30 seconds, think about how you might approach this, and then we'll go through it together. Say this is 1 second, this is 2 seconds, this is 3.
What kind of graph are we drawing? Position?
Position time graph, yep. And for this one, we'll assume that you're starting at the origin. Probably the easiest way to approach these graphs when you're going from velocity time to position time is to use little dots to show where you're going to be on this position time graph at any point in time. So like at the beginning, we know we start at the origin because we said originally that the original position is 0. So if that's true, we know that for the first second, the object is traveling at 2 meters per second. So, if the object is traveling at 2 meters per second for 1 second, where's it going to be after 1 second? 2 meters. So I'll just put a little dot up here at 2 meters. The other way you could think of it is because this is your velocity, on a position time graph, the slope represents velocity. So because we've got a velocity of 2 here, we're going to have a slope of 2 for the first second. So that's another way to think about this. Whatever's easier for you. So that would be the first second. Now from 1 to 2 seconds, we've got a velocity of 0. Obviously that means we're not going anywhere for that second. So at 2 seconds, our position has not changed. We're still at 2 meters. Now from 2 to 3 seconds, we're moving at -1 meter per second. So of course that means if we're moving at -1 meter per second, that we're going to be, after this second, 1 meter closer to the origin, because negative means you're going back towards the origin. So that's what you would have at 3 seconds there. I suppose I should move it up a little bit here. That's a little bit more accurate. But yeah, you can think of it in one of 2 ways. Think of it in terms of where the object's going to be at that period of time. You know, if it's going at -1 meter per second, that means after the next second, it's going to be 1 meter closer to the origin. Or you could think of it in terms of slopes. This is a slope, or this is a velocity of -1. So on our position time graph, we're going to have a slope of -1. That's the sort of thing you'll see on page 2. On that page, you want to make sure you take your time. Should have plenty of time to work on this test. Page 3 features another position time graph, kind of like page 1, except at least one of the objects will be moving with an acceleration or a deceleration. So that might be the graph that you're given. Now from this graph, you'll be asked to answer some questions, and the way that you answer those questions needs to be listed like this. So one of these 3 ways is how you have to answer the questions on this page. So let's see here. What about the displacement at 3 seconds? The displacement at 3 seconds. So what do you think about that one? At 3 seconds, is A greater than B, A less than B, or A equal to B? Equal, exactly. Because at 3 seconds, they are both in the same spot. They're both in the same position. So that means A will be equal to B for this one. How about average velocity from 0 to 3 seconds? Equal, absolutely. And your average velocity from 0 to 3 seconds is going to be equal. And the reason for that is because both of these objects start at the same position, and both of these objects end at the same position at 3 seconds. So remember, average velocity is just change in distance over change in time. They've both had the same change in difference over that same period of time. So average velocity is going to be equal. How about instantaneous velocity? The actual velocity at 3 seconds. So what do you think on this one? Is A greater than B, A less than B, or A equal to B? A is less than B, absolutely. Because you can see the slope of A is pretty much 0 at 3 seconds. The slope of B is definitely positive there. So in that case, A is less than B. Very good. Further questions on this one? Wonderful. The other questions are just going to be position, velocity, and acceleration time graphs, and jumping among those three. One thing I will tell you for sure that will be on the test from this section. Do you guys remember before Christmas break, we did that class-wide stacks activity? Kind of looked like this. Okay, so here's the thing. On the test will either be this page right here, the first page of that activity, or the second page of that activity. So, make sure that you understand that. It might be a good idea to review these pages. Now, chances are you probably don't still have this sheet in your possession, and that's okay, because it is available on Schoology. It's called Velocity and Acceleration Stacks Activity. Both the activity and the answer key is posted on Schoology. So practice with the graphs that aren't on there, and then check your answers with the answer key. Obviously, the answer key can be found in the answer key folder. The actual activity is found in the regular, velocity and acceleration folder. So make sure you're aware of that. Let's just go through some of these examples, and that'll be it. I can't emphasize enough how important it is that when you're studying those graphs, hopefully you take a look at them between now and the test, but what will not help your studying is if you just look at the answer keys and try and remember them. That will not help. I know that from personal experience. So the best way to study for this section of the test and any section in physics is to attempt the problem, get as far as you can, and then check your answers afterwards and fix what needs fixing. And you keep doing that until you continue to get consistent right answers. That's the best way to study for this test, and it's the best way to really study for any test in physics. So, we've got 3 graphs, and we'll just kind of start with some random things here, and hopefully you guys will be okay. All right. There's our position time graph. I'll give you 1 minute. Try and fill out the other 2 graphs. So as I've mentioned in the past, it's all about the slopes on these graphs. Obviously, you can have your formula sheet with you. Tomorrow might be a good day to wear your formula t-shirt. So I encourage everybody to wear their physics t-shirts tomorrow. You guys did a good job designing those. Wear with pride. And the good part is that the equations and the information you need is on the front part of that t-shirt. So it's just a matter of looking down at your motion box. So we've got a slope that begins with 0, and on a position time graph, the slope represents velocity. Because we start with a slope of 0, that means we'll begin with a velocity of 0 on this graph. As time goes on, our slope grows in the positive direction. Therefore, our velocity will grow in the positive direction. The other part of this is once you have your velocity time graph, in the same way that the slope on the position time graph represents velocity, the slope on a velocity time graph represents acceleration. So this is a constant, positive slope, which means we've got ourselves a constant, positive acceleration. That's one example. We'll see how many of these we can get through by the end of the hour. Now, of course, you're not just going to get position time graphs on these. It might begin with a velocity time graph. Try this. "60 seconds. Once again, it's all about the slopes. So we begin on our velocity time graph with a big negative velocity. So we know in our position time graph, we got to start with a big negative slope. So because of that, I'm going to start up top here somewhere. Maybe up here. So we're going to begin with a very steep negative slope. And you can see what happens to that velocity as time goes on. The velocity decreases, ultimately reaching 0. So that means from this big steep slope, our slope will decrease, ultimately reaching 0. So something like this. On the acceleration time graph, we've got a positive slope here. So that means we'll have a positive acceleration. So there we go. Let's keep practicing some of these where we begin with the velocity time graph here. Try this. So we are going down diagonally, and then we continue at 0 for a while. So see what you can do with this guy. 60 seconds. So for this one here, you can see we begin with a large positive velocity. That means over on this graph, we're going to start with a large positive slope. As time goes on, the velocity decreases, ultimately reaching 0. So our slope will decrease, ultimately reaching 0. Now, from here to here, you can see we continue to have a velocity of nothing. So what that means on your position time graph is once you get to the point where your slope is 0, you can just continue that slope for a while. So there you go. So this dotted line represents, this portion and then that portion. Of course, for the acceleration time graph, we've got a negative slope, so that's a negative acceleration. We've got a slope of 0, so that's an acceleration of 0. All right. Don't give up on this one. This looks intimidating, but we'll go through it together. See what you can do with that in 60 seconds. If you didn't get through it, that's okay. Just want to make sure we have time for one more after this. It looks confusing, and usually it's this 0 point where folks get a little confused on this one. So just take it one step at a time. Remember that this graph is going to tell you about the slope on the position time graph. And let's just start right from the beginning. We begin with a velocity that's big and negative. That means we're going to start over here with a slope that is big and negative. Maybe something like this to start. As time goes on, the velocity decreases, ultimately reaching 0, which means that this slope will decrease, ultimately reaching 0. Now, after that 0 point, the velocity grows in the positive direction. So that means over here, your slope is going to grow in the positive direction. And you've got yourself a cute little happy face. And that's all this velocity time graph shows. Again, it's all about the slopes, folks. This is a constant positive slope here, so this will be a constant positive acceleration. Yes?
If we draw the happy face on the test, will we get extra credit?
Maybe like a point or something.
Might give you an extra point.
But is there like gonna be this one?
There could be. I don't know. I can't tell you. But just make sure to include the nose and the eyes if you draw a happy face. All right, last one. Let's go back to the position time graph here. Let's say we have a graph that looks like this. So it's curving up at the beginning, and then maybe right about here, that curve stops, and we've got just a constant diagonal line. See what you can do with that. 60 seconds again. All right, so with the last minute or so we have, let's take a quick look at this one. It's all about the slopes. We begin with a slope of 0 on this graph. That means over here we start with a velocity of 0. As time goes on, my slope is growing. So my velocity grows. Now here, my slope stops growing. It is a constant positive slope from here on out. So what that means on my velocity time graph is that once we reach this point, the velocity stops changing. So whatever value that velocity would correspond to over here is not going to change. So we have that constant line. In terms of the acceleration time graph, positive slope, so that's a positive acceleration. Slope of 0, that's an acceleration of 0. And that is how we do that. If you have trouble finding those stacks, sheets, or answer keys, feel free to message me or let me know. Happy to direct you there. Good luck on the test tomorrow. I smell a lot of A's out there on this.